In this section, we will learn about eigenvalues and eigenvectors. Let me start with a very simple observation. Consider a square matrix 1, 1, 2, 0. We can look at this matrix as a description of a function or map from R2 to R2. We can consider a function f from R2 to R2 defined by x, f at vector x is equal to the vector a times x. That means we have two arguments, the old vector x arrow, and we perform some computation and we get a new vector, the result. In particular, if we denote the result by arrow, then this is a times x arrow, and this is 1, 1, 2, 0. And if we denote the coordinates of x as x1, x2, then this is x1 plus x2, and the second coordinate is 2x2. Let's have a look what is the effect of this map on a few chosen vectors. Consider the vector e1 being 1, 0. That means a unit vector in the direction of the first coordinate axis. What is the result of this? If we consider the matrix 1, 1, 2, 0 and multiply by the vector 1, 0, then we get 1, 2. This is always the case when we take a matrix and multiply by a vector which has all the zeros, just one single coordinate equal to 1, then this vector maps to a vector which is exactly the column of the matrix in such position where there were 1 in the vector. So this vector 1, 0 goes to vector 1, 2. So this is the effect of this matrix, or this map, on this vector. It is longer and it is rotated to the left. We say in the counterclockwise direction. In mathematics we call this direction positive direction, positive orientation. Okay, remember that. What about the vector E2, which has 1 at position 2? The result of this vector will be 1, 1, 2, 0 times 0, 1, which is now, the second column. It happens to be E1, but this is not important in this case. How can we visualize this result? The vector 0, 1 is here, and the vector 1, 0 is here. So this time, the length of the vector is the same unit, but now it is rotated in the opposite direction, in the clockwise direction. In mathematics we call it negative direction. So if there are some vectors that are rotated to the left, some vectors that are rotated to the right, a natural question arises whether there is a vector which is not rotated, which stays in the same line. This is a very important question. So we want to find a vector, let's call it V, such that the result is parallel to the vector itself. And this appears to be a very important question, and the solution will be very useful. So one vector here, they should be parallel, that means in the same line. That means they must be either equal or one of them is a multiple of the other. Lambda is some number, some scalar, and taking a vector v arrow and multiplying by a scalar, we may prolong or shorten the vector, but it stays in the same line. If lambda is negative, it goes to the other orientation, but in the same line, and that's important. So we want to find a vector such that when multiplied by a matrix has the same result as if we multiply the vector by a scalar, by a number. That means in the same line. And we assume the matrix A is given. So we have, say for a 2 by 2 matrix, we have how many equations and how many unknowns? One unknown is lambda, and for a 2 by 2 matrix we have two unknowns, the two components of the vector. So we have three unknowns. And how many equations? This is an equality between two vectors. That means two equations. It looks like there will be more than one solution, right? If we have more unknowns than equations, we can expect more solutions than one. Well, okay, we can manipulate this a little. We can subtract lambda v. If it were just numbers, then we would probably factor out v. But if we factor out v here, we get matrix A minus number lambda. It's not okay to subtract or add objects of different kind, numbers and matrices. But we can write E here where E is the identity matrix. In the 2 by 2 case, it will be 1, 0, 0, 1. And if we multiply any vector by the identity matrix, then EV is V, no problem. So we don't change anything. And it helps because after factoring out V, we have now the difference of two matrices. And we must factor out to the right. So we have A minus lambda E times the vector V with the vector 0. Now, let's repeat what kind of objects we have here. Matrix, say 2 by 2 or M by M. Number, scalar. Matrix, the same size. Number times matrix is matrix. So this product, lambda E, is a matrix, and this minus is a subtraction of two matrices. So this is a matrix, say n by n matrix. And matrix times vector is vector, and this is equation between two vectors. Matrix times vector should be 0. We've seen this case already several times. This has always one solution, namely V is 0. But V, 0, but this is trivial, this is not interesting. 0 here, 0 here. 0 vector defines no direction. So we want some non-zero vector. That will be much more interesting. Matrix times V is 0, and this should have some non-zero solution. Yes, it has non-zero solution, but under one condition. This has a non-zero, non-trivial solution if and only if, do you remember? The determinant of this matrix must be 0. determinant of this bracket of this matrix A minus lambda E must be 0. And this is the sufficient and necessary condition for this system of equations to have non-zero solution for V. And this equation is so important that it has its name. This is called characteristic equation. Well, and we are almost done. If we are given a matrix A, we write the characteristic equation, which is now equation for one single unknown, lambda. We solve lambda. It may have even more than one solution. And then for each lambda, we solve this system, because now when lambda is known already, this is known, this is known, this is known, and we solve for V. And such a non-zero vector that satisfies this condition is called the eigenvector. In the definition is this, and it should be non-zero. This goes into the definition. And such a number, such a value, lambda, which satisfies this, is called the corresponding eigenvalue corresponding to this particular eigenvector. If there are more eigenvalues, then it may happen that for each eigenvalue we have its corresponding eigenvector. Actually, the word eigenvalue and eigenvector is a composed word, and this eigen comes from German. In German, Eigentum is property. That means a vector that is strongly related to the matrix. It comes from German because when these terms were discovered, then most of the mathematicians, many good mathematicians, were in Germany. Okay, so let's illustrate how to compute, how to find the eigenvalues and eigenvalues for this matrix using this algorithm. So if we have once again the matrix A to be 1, 1, 2, 0, then the characteristic equation is determinant of A minus lambda E is 0. So first let's compute this determinant, A minus lambda E. So this is the determinant of A is 1, 1, 2, 0 minus lambda, and E is 1, 0, 0, 1. So this is 1, 1, 2, 0 minus lambda 0, 0, lambda. And when we subtract these two matrices, we have lambda 1 minus lambda, 1 minus 0, 2 minus 0, and 0 minus lambda. And this can be written just by vertical bars, 1 minus lambda, 1, 2 minus lambda. And this is 1 minus lambda times minus lambda minus 1 times 2, which is 2. And this can be simplified to lambda square minus lambda minus 2. So the characteristic equation is lambda square minus lambda minus 2 is 0. And this is a quadratic equation. So we expect to have two roots, two solutions. And indeed, for n by n matrix, the characteristic equation has the left-hand side, which is also called the characteristic polynomial of the given matrix. This will be always polynomial, and for an n by n matrix, it will be polynomial of order n. Here we have 2 by 2 matrix, so polynomial of order 2. Well, this can be solved by many methods. Say if we compute the discriminant, then we have b squared minus 4a lambda, which is 9. So lambda 1 is minus b, which is 1, plus or minus square root of d divided by 2, so this is lambda. And that means that lambda 1, okay, let's write it here. Lambda 1 is 1 plus 3 is 4 divided by 2 is 2. And lambda 2, 1 minus 3 is minus 2 divided by 2 is minus 1. So we see that this matrix has 2 real distinct eigenvalues, 2 and minus 1. It may happen that the root is double root. We will not discuss this case. And it may happen that the quadratic equation has no real solution and there are only imaginary, only complex roots. This may happen. But for today we will consider only these cases where we have 2 real distinct roots. Well, and then for each eigenvalue, we want to go here and to find the corresponding eigenvalue. So for lambda 1, lambda is lambda 1, we compute this matrix A minus lambda E. A minus lambda E is A was 1, 1, 2, 0 minus 2 times 1, 0, 0, 1. Actually, we don't have to be so explicit. This means that we subtract lambda from the entries on the main diagonal and we leave the other terms unchanged. So we have, okay, if I go this slow way, 1, 1, 2, 0 minus 2, 0, 0, 2. So you see, we subtract 2, the eigenvalue, from the entries on the main diagonal. 1 minus 2 is minus 1. And we subtract 0, that means we leave unchanged these 2 values. And then from 0 we subtract 2. At this moment, it's a good idea to lay down the pen and look at this matrix. This matrix should be singular. It should have 0 determinant. Well, actually, lambda was found by considering the determinant equal to 0. In other words, the rows and the columns should be linearly dependent. If we consider the first, or say, if we consider the second column, then the first column is minus 1 times the second column. So it was good. Yes, so we can continue. And we want to find vectors that, when multiplied by this matrix, give 0. In more scientific words, we want to find the kernel of this matrix, or the null space of this matrix. So if we have the matrix E minus lambda E being minus 1, 1, 2, minus 2, then we want to find some vector, let's call it just xy for the moment. Well, zero vector solves this, but we want some non-zero vector. This corresponds to the set of equations minus x plus y is 0 and 2x minus 2y is 0. Well, as we know, this is a singular matrix, so the equations should be not independent, and this is indeed minus 2 times the first one, so we can forget this. And this has infinitely many solutions. Yeah, do you remember? When we think the number of unknowns and number of equations, we have such a feeling that there will be infinitely many solutions. Yes, there are. This has infinitely many solutions. And we are perfectly happy with just one non-zero solution. So we can take, say, x is 1, and then y is also 1. So corresponding to the first eigenvalue, lambda 1 is 2, we can write the first eigenvector, let's call it v1 with arrow, being 1, 1. And now we do the same with the second eigenvalue. Before we continue, it's a good idea to check whether this is okay. And we can check this by using this line. AB is lambda v. So let's check this. We want to verify that AB is indeed lambda v. So on the left, we have AB. A is 1, 1, 2, 0, and V is 1, 1. And if we perform this multiplication, we have 1 plus 1 is 2, 2 plus 0 is 2. And on the right, we have lambda V, which is lambda is 2, and V is 1, 1. So we have the vector 2, 2. Yes, this is correct. So that was for lambda 1 is 2. And for lambda 2, so let me make some more space here. Lambda 2 was minus 1. Then the matrix A minus lambda E, we don't need a bracket. We subtract minus 1 from the entries on the main diagonal, so we don't have to write all this. 1 minus minus 1 is 2. 1 and 2 are left unchanged because we subtract 0 here. And 0 minus minus 1 is 1. Now again, let's stop for a moment and let's check whether this matrix is indeed singular. Yeah, obviously it is. The first row is the same as the second row. So it has linearly dependent rows, so it has 0 determinant, it is singular. And now we want to find a vector that is mapped by this matrix to 0. So 2, 1, 2, 1 times some vector xy should be 0. The first row corresponds to the first equation, namely 2x plus y is 0. And the second row generates the same equation. We don't have to write the same equation once again. And once again, this has infinitely many solutions, and we will be happy just with one non-zero solution. So we can choose, say, x is 1, and then we find y is minus 2. So the second eigenvector will be 1 minus 2. We can check this. A V2, which is 1120 times 1 minus 2, which is 1, minus 2, which is minus 1, and 2 times 1, which is 2. And when we compute lambda 2 V2, then lambda 2 is minus 1, and the vector is 1 minus 2, which is minus 1, 2. Yeah, the same. So this is indeed another eigenvector of this matrix with the corresponding eigenvalue. Okay, in the next section I will show you a few shortcuts how to do this more quickly, and then some more results and some more consequences.